Alright guys, welcome back. Hope everything's been good so far. Hope the videos are helping you guys out a little bit. Uh, there's one last, or there's two more types of molecule that we need to learn about, really. Three if you count polymers, and I'll go over those in a quick video just so we can have exposure to them. But before that, we have to talk about carboxylic acids. These guys are going to contain a certain molecule shape. And the functional group, the shape is a carbon that's been double bonded to an oxygen, as well as an OH. And this setup is called a carboxyl group. So just like how alcohols have a hydroxyl group, carboxylic acids have a carboxyl group. Pretty simple. And obviously, this can be, I'm just going to put R, that means wild card. So we could have you could put whatever you want on here. You could put just a hydrogen, then you'd have a carboxylic acid that only had one carbon in it, or you could put a carbon with 3 hydrogens attached. You could make that main chain as long as you want. You could spice it up by putting some branches on there. You could throw some double or triple bonds in there. You could throw some halogens. This is why organic chemistry is so cool. This is why I really enjoy organic chem, and I loved doing it in university, particularly the second class that I took, because like we haven't even talked about nitrogen. We're not going to, but you could put nitrogens in certain ways onto these molecules, and it changes how they behave. As a matter of fact, the proteins that your body is made out of, they are made out of amino acids. Those are the building blocks, the Lego blocks of proteins. And amino acids actually have, one end of an amino acid is a carboxylic acid, and the other end of an amino acid is what's called an amino or amine group. So this stuff that we're talking about here actually is used in real life and in life itself quite a bit. Anywho, let's do a couple of examples of carboxylic acids. So remember, you have to have this structure here, the carboxyl group. Now, I'm going to, before we start naming, I'm going to talk a little bit about why this little feature, why the carboxyl group is useful. Now, if you remember when we talked about regular old hydrocarbons, like for example, that's not a very good, it's not a very good H. This guy, so methane. I'll just move these. Oh, it's all together, isn't it? Shoot. Okay, well, pretend I did a better job. CH4. Now, yeah, this thing has hydrogens on it, but these hydrogens do not get to leave. They are stuck on that carbon. They're not going anywhere. However, you notice the name, carboxylic acids. These molecules contain this carboxyl group, and what can happen is that hydrogen that's on this OH, this specific setup, it does not happen with alcohols, well, very, very little. So little that we don't even talk about it. But this kind of structure can drop off that H. And then we know what happens to that H. When we have an H plus and it's in water, we're going to get our good buddy, the hydronium H3O plus ion. So when you see the word carboxylic acid and you're like, how is this thing an acid? Well, this is what we call an acidic proton or an acidic hydrogen. It can fall off. Another way of saying it is the word labile, which means can be removed. So it's a removable H. And here's the little reaction. And it does not happen very often. We would classify all carboxylic acids as weak. Recall from the previous chapter, weak and strong has nothing to do with the concentration of the acid, but it does have something to do with the concentration of hydronium. So if your number up here, for example, for hydrochloric, for HCl, that was 100%, which means that every single molecule of HCl that goes into the water, every single molecule is going to ionize. Remember, acids ionize. And it will form H3O and whatever the leftover ion would be. In HCl's case, it would be a Cl minus ion. How do we predict those? The acid-base table in our data book. So anyways, these guys are weak acids. They are used all over the place. Let's take a look at the simplest one. Pardon me. In this case, the R, the wild card, is just going to be a hydrogen. So looking at this, we know that things that have single carbon, they start with methane. That's from the base word of methane. But this is for sure not methane. This is, even though it's got one carbon, that's pretty much all methane and this molecule have in common. Because it contains this carboxylic acid group, it gets the ending oic acid. And there's a space between here. So this is methanoic acid. Methanoic acid, a little bit of an interesting bit of info about it. In normal people speak, so not science people speak, sometimes this is referred to as formic acid. Those of you who know French know that the word ant is fourmi. And you know me, I love getting into like why words are the way that they are. And yeah, the reason why it's called formic acid is literally because some species of ant make this stuff and they use it as a chemical weapon, as a defense. The next time you're out camping, or you know, you're in your backyard and you see that part of your deck is starting to rot away or something like that, and you see ants crawling around, the big ants, those big boys called carpenter ants, they produce formic acid. And the way you can tell is because if you ever tick them off, if you ever like start flicking them around and you're like, I did this when I was like 8, 9, 10, 11, you know, when you're a kid, you just bothering nature to see what it does. And these guys make a smell. And it's a very, it's, how would I describe it? It's like spicy vinegar. it's like vinegary. It's kind of got that acidic twang to it, but it also has like a little bit more of a pungency. Like it almost like stings your nose a little bit. So you can imagine that if you were a smaller animal uh, trying to maybe eat some ants, or bugging an anthill. I don't know why an animal would do that other than to get food, but there you go. What happens is all of these ants will put their little abdomens, their backsides in the air, and they will spritz out little tiny spritzes of formic acid. If you've ever taken a lemon peel and like bent it the wrong way, and you can see little drippies of lemon oil from the lemon peel shoot out, it goes like pfft, little tiny sprites. That's kind of what you would see. And yeah, it's got a very pungent smell to it. In Central American cuisine, um, I think it's Oaxacan cuisine in Mexico. Um, they're the most untouched by the invasion of Christopher Columbus and the European imperialists and colonialism. And because of that, they use a lot of traditional foods. And there is a salsa that is made out of the backsides of ants that make formic acid. So it would be like very vinegary, but maybe a little bit more punchy. Fascinating stuff. Anyways, let's move on. I'd love to try it, by the way. That'd be so cool. All right, let's tack another carbon on there. So let's go like that. We've still got our carboxyl group, but now I'm going to add another carbon. And of course the hydrogens that come with it. So now it's two carbons, so there's our two carbons there. We know that the root word would be ethane. If this didn't have all the cool oxygen and OH on there, it would just be called ethane, right? But since it's got that carboxylic acid, that carboxyl group, it gets the ending oic acid. Simple, right? Like not a complicated naming system. But here is where it's going to get a little bit funky. Oh, an ethanoic acid, that is also called acetic acid. That is the main component of vinegar, which we use for a lot of different reasons. Primarily like pickling and making and adding to food for flavor. So very cool. Like this is a useful chemical. It's also used a lot in the preparation of chemicals for industry, because you can do some fun chemistry with this little side over here, this carboxyl group. So let's add another carbon, and after that we're going to get weird. We're going to start adding some other stuff just for funsies. Or rather, after that we'll start playing around with the structures. So 3 carbons, and so this is going to be, oops, if this was just hydrogens and nothing else interesting, no O, no OH, this would be propane. So propan, and then since it has our carboxyl group, sometimes this molecule actually, I personally don't agree with it, but this is how we're supposed to teach it, and this is the science, so I have to be correct. This is actually called propionic acid. Sometimes if you go check your maybe if you have liquid shampoo or liquid or like um, liquid soap, you might see this. Propionate. That means that it contains this component, this molecule. So you might be asking yourself a question. Can't we attach this C double bond O OH to another carbon? And we can. But in order to do that, we're going to have to go to one more carbon in length. So I'm going to have 1, 2, 3, 4. So if we put our carboxyl group on the end, and I'm just going to fill in the rest of the spaces with hydrogens as usual. This is 4 carbons, so that's butane. So butan is our start. And then, because it's got this feature, it gets the ending oic acid. Let's try putting a branch onto one of these carboxylic acids. I'm just going to move everything up a little bit. I don't have the ability to make the page longer. For some reason, they just don't let you do that after a certain point of scrolling. So I'm just going to scoot all these up. And let's redraw. So let's consider this one. C double bond O, and then an O H. Remember, we always have to obey the bonding capacity. We always have to make sure that every C has 4 lines coming out of it. Every O has to have 2 things bonded to it, or 2 lines coming out of it, and every H has 1. So my oxygen here, it has both of its bonds spent. The oxygen here, one bond is spent for the carbon, one of them is spent to bind to the hydrogen. So now what do we do? Well, we still have to get a main chain, and the main chain has to include the interesting thing. And that's always how it works. That means our main chain has to be something like that. Remember, for this, we only count the carbons. You don't count this and be like, oh, this is a hexane because there's 6 things. No, it's just the carbons. So we have 3 carbons here. So this is going to be, propionic acid. But then we have this branch, and I mean, the branch is on carbon number, what carbon is it on? Would you be terribly surprised if I said you want to count starting at the C double bond O OH? You want to start on that carboxyl carbon. It makes sense. It's the most interesting component in this molecule. So 1, 2, 3. So that means that this is a methyl group on carbon number 2. So we would give this the name 2 dash, oh no, I'm going to run out of space, shoot, methyl, 2-methylpropionic acid. And so your carboxyl group always has precedence or priority. So I'll see you in a couple of minutes, and we're going to be talking about esters. And again, I'm really, really bummed that we can't do the ester lab because it's so much fun. Sorry.